Alright everyone, another optimization problem. This one here is a bloody classic. I believe it's the first one I started off doing when I took optimization my first time for AP Calculus AB. So you are given a 1 foot square of metal, which is to be made into a box by cutting squares out of corners and turning up the edges. The question is, what dimensions will maximize the volume of this metal box, this metal cube or cuboid, and what is the maximum volume? So we know that this square, this metal sheet, is going to be dimensions 1 foot by 1 foot. But the neat thing is, given that we're cutting off squares of identical side lengths on the corner, we can just call these squares, we can let these squares have dimensions x by x at each side of the corner. So therefore, if we were to take a look at the length and width of this volume, it would correspond to the total distance, the total length of the 1 foot of the metal sheet being subtracted by 2 of these unknown square distances over here. So we end up getting 1 minus 2x to be equal to both the length and the width of this metal box over here. Now what is the height? The height is easy. If we're going to go and fold everything up piece by piece, like here and so, this height, x, this x segment is going to project itself up. Same with here in this direction. So this gets folded up here, this gets folded up here. So we end up with a height for our box of length x. So if I were to draw what the final volume looks like, it would be x here, one minus 2x, and 1 minus 2x. And we know that the volume of a prism is length times width times volume. So we can easily put in these corresponding lengths in there. 1 minus 2x times 1 minus 2x. So we get a cubic, which we can then simplify out, which becomes, according to me, simplify this out over here to x times 1 minus 4x plus 4x squared. This becomes x minus 4x squared plus 4x cubed. And now we do the usual thing, take the derivative of this volume function with respect to x. So this is v of x. If I do dv dx, now it's going to become 1, that's going to become, bring the 2 down, minus 1 at the exponent, that's minus 8x plus 12x squared. But before we go on, I want to go and take the second derivative here because we want to find dimensions that maximize the volume. And when we take the second derivative this time, we're no longer going to get a constant number, which is either positive or negative. We're going to get a linear function. So we have to go and solve that in terms of an inequality. So we want d squared v dx squared to be less than 0. And that, from here, is going to equal minus 8 plus 24x. So we want that to be less than 0. If we go and solve that inequality, we'll get that x will need to be less than 8 over 24, which is equal to 1/3. So that would be useful to us. Now we can find the actual lengths, the actual heights, dimensions, critical points, which will optimize the dimensions of this metal box by saying this equal to 0. So 0 equals 1 minus 8x plus 12x squared over here, as so. And you might wonder, can we factor this expression out? Factoring is the best way to solve a quadratic equation, but you could do other methods as well. One way you can tell if that is the case, if it is indeed factorable, is by checking the discriminant of this quadratic equation, which is delta equals b squared minus 4ac, where b, a, and c correspond to the coefficients of the quadratic in standard form. So from here, it's going to be minus 8 squared minus 4 times 12 times 1, which is 64 minus 48, which is, I can't do mental math, that is 16, which is indeed a square number. So we know if it's a square number, the discriminant is a square number, that this can be factored out easily. So what we need to think of is what two numbers multiply together to give me 12x squared, but when I add them up together, give me minus 8x, and when I multiply them, give me positive 1. So we know that 0 is going to be of some form a1 x plus b, a2 x plus b1 plus b2. So yeah, this is 12. So what two numbers a1 and a2 multiply together to be 12? What two numbers b1, b2 multiply to give me 1? And what are these numbers such that when you multiply and add them, add the linear terms together, you get minus 8? There's only one answer that works for that, and that is, where is it? Yeah. For this, for 12, it is 2 times 6, which gives me 12. And if I get negative 1 times negative 1, that gives me positive 1. If I therefore get 2 times negative 1 plus 6 times negative 1, that will give me minus 8. And so this quadratic can be factored out into 0 equals 2x minus 1 times 6x minus 1. And now, setting each of these factors equal to 0, we get that x either equals a half or x equals 1/6. But remember, from our second derivative constraint inequality, x has to be less than 1/3. So this x equals 1/2, we ignore it from our solution. So x equals 1/6 is the appropriate height, or rather missing variable, which will maximize our volume. And as we know, 1/6 corresponds to the height, so solving the first part of the question, the height equals 1/6 of a foot. The width equals 1 minus 2 times 1/6 of a foot, which is equal to 2/3. You could check this out from this. 4/6, 2/3 of a foot. And that is the same thing for the length. So it follows the same equation. So this is 2/3 of a foot. So the ideal mental sheet which would work out for this configuration is 1/6 feet by 2/3 feet by 2/3 feet. And now to find the actual maximum volume, just multiply these numbers together. Part 2. Box the answer here. That becomes 2/3 times 2/3 times 1/6, which is equal to 2/27 cubic feet. And you can expand that out into decimals if you want. So that's it. That's essentially the problem done. Now here's a little extra challenge for you. We've had this setup where we're given that the sheet that we're dealing with is a square of 1 by 1 foot. But now let's switch it around. What if the square sheet we know is of unknown length, x by x, and the corners being cut out, each of those are 1 feet? What would then be the dimensions that will maximize the volume? And what will be the maximum volume in this case? If you're interested, try that problem out, write down your solutions, post them in the comments, and I'll go and check on them if I have the chance. Until then, this is the Proof Essayist signing off.